of efficient classical computation. That evidence relies on additional conjectures beyond that the polynomial hierarchy does not collapse. Okay, but in some work that Sergey and Robert and I did in 2017, we addressed a complementary but less ambitious question, and we showed that constant depth quantum circuits are strictly more powerful than constant depth classical circuits. So this does not rely on any conjectures, but it does not address this larger question of whether or not you can do something outside of efficient classical or polynomial time classical computation. And so here's what we proved, and after this, in the rest of the talk, I want to tell you about more recent follow-up work. But for now, let me just review what was shown in 2017. So we showed that there is a computational problem with n input bits and n output bits, which is solved with certainty by a constant depth quantum circuit composed of geometrically local gates in 2D. So there's a constant depth quantum circuit, it solves the problem with certainty. But on the other hand, if you have a classical probabilistic circuit composed of bounded Fannin gates, and it solves the problem with high probability, then the depth has to be increasing with n. Okay, so the separation is constant depth quantum versus you need at least log depth classical to solve this problem. Let me just explain some of these terms. Classical probabilistic circuit, it's a deterministic function, like a circuit C sub n, which is given random bits at the input. That's what I mean by a classical probabilistic circuit here. What is the fan-in of a gate? So remember that in the quantum case, we're considering circuits composed of, say, 1 and 2 qubit gates. And so to make a fair comparison, we restrict our attention to classical circuits where every gate has at most a constant number of inputs. The fan-in of a gate is the number of inputs that it takes. And we're going to consider the case where that fan-in is upper bounded by a constant. Finally, what is this computational problem? Well, I'm not going to talk really much more about it because I'll give you another example in the next section of the talk. But you can think of it as a non-standard linear algebra problem. And it has the feature that it can, in fact, be solved efficiently, that is in polynomial time, using a classical computer. But our result shows that that polynomial time classical computation can't be parallelized to constant depth. Finally, this feature that the quantum circuit is composed of geometrically local gates in 2 dimensions, that's something that we're going to improve upon later. So I just want to draw attention to that. OK, so this was our 2017 result. And the key insight was that the computational power, in this case at least, stems from quantum non-locality in the following sense. So first, let's think about classical constant depth circuits and their limitations. So a classical constant depth circuit like this one, where every gate has bounded fan-in, it's a local function in the following sense. We can take any output bit and trace all of the input bits that can affect the value of that output bit. So we trace back through the circuit. Every time we go back through a layer of gates, we expand the size of this light cone or this causal cone by a factor of the fan-in. And so the total number of input bits that determine the value of that output bit is at most the fan-in, which is a constant, to the power of the depth, which is a constant. So in other words, every output bit is determined by a constant number of input bits. And this is what I call a local function. And this contrasts with what you can do with constant depth quantum circuits. So a constant depth quantum circuit, so here's an example where you have, for example, a circuit that takes some input x. It also has some data qubits initialized in 0. And I claim that before measurement, you can prepare a state psi sub x. And then after measurement, you get a probability distribution over bit strings that depends on x. And the input-output statistic, so this distribution p of z given x, cannot be reproduced by any local function. So that is somehow the sense in which quantum non-locality appears. And we'll see another example of that in a few moments. Okay, so since our work, there have been some extensions and generalizations. Our original paper, we showed worst case lower bound, meaning that we could establish this lower bound on the classical circuits only in the worst case, but it was later shown both in work of Legal and also in the supplementary material to our published version of our paper that it's possible to show an average case lower bound. Kudron, Stark, and Vidic showed that you can use the assumption that your device has constant depth to certify the randomness that's generated by the device. This restriction that we compare against classical circuits of bounded, with gates of bounded fan-in, was lifted by Bene, Watts, Kothari, and Schaefer and Tull in a paper that has yet to appear, I believe, but which has already been has appeared in some conferences. And they consider unbounded fan-in and or not circuits. And they show that a similar lower bound holds in that setting as well for a slightly different problem. We also, in our lower bound, we have a sort of weak bound on the classical success probability. Like we say that if the circuit succeeds with high probability, say greater than 7/8, then the lower bound holds. But that threshold of 7/8 has been lowered to something that decreases exponentially with n. And finally, in our most recent work, we show that the two-dimensional quantum circuit can be replaced by a one-dimensional quantum circuit. We also show that a separation of this nature can be achieved in the presence of noise. And those are the two things that I'm going to talk about in the remainder of the talk. Okay, so in this part of the talk, I'll talk about quantum advantage with one-dimensional quantum circuits. And if you haven't seen the previous work and were confused about, maybe how this arises, this will give you some flavor of it. Okay, so the first thing I'm going to describe is a non-local game, which many people, I think, in the audience already know. And so I apologize for repeating it. The game is based on Merman's magic square, which is a 3x3 square. And a classical assignment would be a way of filling out this square with plus minus 1 variables so that every row multiplies to plus 1 and every column multiplies to minus 1. So we can put a variable in every square, and then we have the row constraints on the side, and we have the column constraints on the bottom. And you can easily see that this is just not possible, because if we multiply all of the row constraints, if we take all of the constraints that are written on the side and we multiply them all together, we get that every entry, the product of all the entries is 1, but if we multiply all of the column constraints together, we get that the product of all the entries is minus 1. I'm going to stop using this pointer. So this is not possible. On the other hand, we can consider a slightly more general thing called an operator assignment. Here, the goal is to fill the table with operators that square to the identity and commute within every row and column, so that every row multiplies to plus the identity and every column multiplies to minus the identity. This is a related but different task. And here is an operator assignment involving 2-qubit Pauli operators. Okay, so you can check that every row multiplies to plus the identity, every column multiplies to minus the identity. So there is some sense in which the quantum version of this classical assignment thing can be done. And that directly leads to the possibility of winning a game defined as follows. So we have two players, Alice and Bob, who can't communicate. And Alice is given a column label, and Bob is given a row label, 1, 2, or 3. And they have to spit out the entries that they want to fill out that column or row with. And their entries have to multiply, Alice, since she's filling out a column, her entries have to multiply to minus 1. Bob, since he's filling out a row, his entries have to multiply to plus 1. And they're going to win the game if they agree on the square where they overlap. Okay? So this would be, you should imagine them filling out this table, one row and one column, and they have to agree on the square where they overlap. And classical strategies fail because any classical strategy is no better than agreeing beforehand on a classical assignment to the entries of the magic square, and we just argued that that was not possible. In fact, the best you can do is to win with probability 8/9. On the other hand, there is a quantum strategy which wins with probability 1. When I say a quantum strategy, what I mean is that Alice and Bob are allowed to share entanglement. So here, these purple bars indicate bell pairs. So they share 2 bell pairs. And the strategy that Alice and Bob use is Alice, when she's given her column label, will measure the commuting operators in column alpha. So if she was given alpha equals 1, she would measure x tensor identity, I tensor z, and minus x tensor z, which, since they're all commuting, can be measured simultaneously. And she would output those measurement outcomes. And Bob would do the same thing with a row. Now, it's easy to check that that will always satisfy the winning condition of the magic square game. So this is a quantum strategy which wins with certainty, even though you cannot classically win this game, even with shared randomness. Okay, so that's all sort of standard. But now I would like to show you how this 2-player non-local game can be embedded into a task involving multiple qubits. Okay? So let's imagine, just for the purpose of this talk, I'm going to call this the 1D magic square protocol. Okay? So this is just some protocol that some quantum players can do. So we're going to have a bunch of Alices and a bunch of Bobs. Okay? And they're going to be arranged in a line like this. And like B1, Bob 1, is nearest neighbors with Alice 2, you see, because they're really right next to one another. And Bob 2 is nearest neighbors with Alice 3, okay? Alice 1 doesn't have a neighbor, and Bob 3 doesn't have a neighbor. And we're going to allow the nearest neighbor pairs to communicate. Everybody is going to be given an input, which is an integer from the set 0, 1, 2, or 3. And we're going to imagine that they follow the following protocol, okay? So if you and your neighbor both get 0, then just merge with your neighbor and measure x tensor x and z tensor z on both pairs of adjacent qubits. So that would be like if Bob 1 and Alice 2 both got 0, they would measure x tensor x on this pair of qubits and z tensor z on that pair of qubits, and the same thing on this pair of qubits. And that performs an entanglement swapping measurement, if you know what that is. Now, if they were to get 1, 2, or 3, then just act as if you're playing the magic square game. Okay? So you do the measurements in the row or column, depending on whether or not you're an Alice or Bob. So if you get 0 and your neighbor gets 1, 2, or 3, or if you don't have a neighbor, like you're on the end, then just measure your qubits in the z basis. That corresponds to just basically, you just output a random thing, because you're measuring half of a bell pair in the z basis. Okay? So let's see what happens in some example if we follow this protocol. So here's an example, and there's only 2 non-zero entries in the input. And we're going to, like these players on the left here, they're just going to measure in the z basis, so they get some random outputs. And for the purposes of this discussion, we're going to ignore them and their outcomes. So we're left with this. And so those 2 players in the middle, Bob 2 and Alice 3, they're nearest neighbors, and they both get 0, which means that they're going to perform entanglement swapping measurements. And they get some outcomes, which are just some numbers s, t, s prime, t prime. But the point is that these entanglement swapping measurements transform the state shared by Alice 2 and Bob 3 into a Bell state up to a Pauli correction. So it's an EPR pair up to a Pauli correction. So I've written it as a different color than the original one, because it may differ by a Pauli correction that depends on the measurement outcomes s, t, s prime, t prime. Now those players are now instructed to play the magic square game. But they have possibly a different entangled state than the one that we talked about earlier, the EPR pair. So they're playing the magic square game with a Bell pair up to a Pauli correction that depends on these intermediate measurements. And their outputs will, if you modify the winning condition of the magic square game, then their outputs will satisfy that modified condition. Okay. So more generally, let me just generalize this a little bit. More generally, if we choose an input with only 2 non-zero entries corresponding to 1 Alice and 1 Bob, we can force any Alice and Bob pair to play a modified magic square game, because everybody to the left of the first non-zero entry we can sort of throw away, and then everybody in the middle does entanglement swapping measurements. The Alice and the Bob we selected are left with some maximally entangled states that depend on the measurement outcomes in the middle, and their measurement outcomes, their input-output statistics will win a modified version of the magic square game. Okay. So now we can define what we call the 1D magic square problem. And the problem is, we're given an input x. Your goal is to find an output z that occurs with non-zero probability when running the protocol I just showed you. Okay, that's the problem. It's a relation problem, because for every input x, there could be multiple outputs z that are solutions. And it's easy to see that this 1D magic square problem can be solved with certainty by a constant depth quantum circuit. The constant depth quantum circuit, I mean, I just reproduced a figure from our paper, which you're not really supposed to parse. But the point is that the constant depth quantum circuit just simulates the protocol that I just showed you. And it only uses geometrically local gates in 1 dimension. That should be sort of intuitive, because the protocol we described really is only local in 1 dimension. And we also can show a classical lower bound, which states that a classical probabilistic circuit with bounded Fanon gates, so Fanon at most k, say, which solves this problem with high probability, must have depth increasing logarithmically with n divided by twice log k, and if k is a constant, this is omega of log n. The proof idea is to look at this subset of inputs we talked about earlier, where we can force any Alice-Bob pair to play the modified magic square game. For the classical circuit to solve the problem, the input-output bits of the chosen Alice-Bob pair have to be causally connected in some specific way that I did not describe. But a low-depth classical circuit is a local function, and every output bit can only be causally connected to order 1 input bits. But there's order n squared Alice-Bob pairs. So this is sort of the idea of the proof, and the actual proof is a little bit, but not too much more complicated. Okay, so that concludes the first part of the talk. And now I would like to tell you about kind of our main result, which has to do with the extension to noisy constant depth circuits. So here is what we show. We show that the same sort of thing holds even when the constant depth circuit is implemented in a noisy way, and I'll describe what kind of noise I mean in a moment. The classical lower bound is slightly weaker. We get a lower bound of log n. That should be omega of log n divided by log n. So that this log n in the denominator makes it a little bit weaker than the log n bound we had before. I also am only going to mention on this slide that the constant depth quantum algorithm that we give can be implemented in 3 spatial dimensions. But that is too much for me to explain in this talk. Okay. So first of all, let me just describe why noise is a problem. Like, why is this something that we even needed to do or wanted to do? So the circuit which solves the 1D magic square problem, I didn't go into this, but the circuit which solves the problem for every input x is a Clifford circuit. In fact, you can write it as a circuit where it's a controlled Clifford circuit where every gate is a controlled Clifford gate controlled on a few bits of the input. Okay, so although actually that's not relevant for the next sentence, it will be relevant throughout the rest of this section of the talk. What is relevant is that we have n output bits that we want to measure. And in the presence of noise, even if we just had noise on the output, with noise rate p, there will be roughly p times n output bits that are corrupted. So we cannot expect a noisy circuit to give us a solution. So we have to, in the rest of this section, we have to understand how this kind of circuit can be modified to be resilient to noise And in fact, we're not going to be able to do that, so we're going to have to come up with a different solution. Okay, so what is this noise model? And I'm not going to, I don't really want to get into the details here, but we use a very broad family of noise models called local stochastic noise, which include simple independent noise models, but also allow for correlated noise. The main thing is that they, like most noise models, have some parameter p, which is the noise rate. And so we're imagining that at every layer, after every layer of gates, a random Pauli is applied with noise rate p. What are the challenges with naively using quantum error correction? I mean, that would be the natural thing to try. Would be to take the circuit I showed you before, encode every qubit in a quantum error correcting code, apply a logical constant depth Clifford, and then measure all the physical qubits and then decode to get the answer. This will certainly work in the sense that it will, protect the information, and if you use the codes with the right distance and so on, you will be able to produce a bit string that solves the problem. One first thing is that if we want things to remain constant depth, then we should certainly try to choose a code where this logical constant depth Clifford in the middle can be made constant depth. And one way to do that is to ensure that the 1 and 2 qubit logical Clifford gates can be performed by constant depth circuits in the code. But we still, because we need the entire n-bit output string to be correct with high probability, we want the probability that each of these that there's an error in each of the code blocks to be decreasing with n. And that leads to two problems, what I call the encoding problem and the decoding problem, which are basically that neither of these operations can be done in constant depth for a good code. That we can neither encode the logical information, nor can we decode the information in constant depth. So although this will produce this will protect the information if you just encode in an error correcting code, you cannot preserve the depth of the circuit in this way. So now I want to tell you how we overcome these two problems. So how do we get around the decoding problem? So the decoding is a purely classical post-processing step. So we take the measurement outcomes from all of the code blocks, all the physical qubits, run them through some classical function, and we get a bit for every code block. Now, remember that our ultimate goal is to generate input-output pairs that satisfy this relation, like this problem, the 1D magic square problem. So we're given x, we want to find z such that r of x z equals 1, where r is the function that defines the 1D magic square problem. But since the decoding is classical, we can just imagine defining a new relation that does this classical post-processing for us. So imagine defining a new relation r prime, where now r prime takes the input x and all the physical the measurements of all the physical qubits y. And we're just going to define that relation is 1 if and only if the original r of x on the decoded y is 1. So now we're just forcing the relation to decode for us and then compute the original relation. Okay, so this seems like a decent solution, although it's not clear how it affects the classical complexity of this problem. And we'll talk about that in a moment. Okay, but then we have the encoding problem, which is a little bit trickier. The encoding operation takes m physical qubits and prepares a logical qubit encoded in some error correcting code. And that can't be done in constant depth. But if we have a low depth parity check stabilizer code, then it is possible to measure all the code stabilizers in constant depth. So we have the original m qubits of the code. We have some ancilla qubits that are used to do the measurements. And now we output the measurement outcomes, and we also output the encoded state up to a Pauli correction, which I'm calling rec-s for recovery. Because normally what you would do in error correction is you would apply that recovery operator to correct. Right? This is the correction you would apply. It depends on s. Okay, this can be done in constant depth. Now, because the circuit for every input is Clifford, this Pauli rec S, it's not such a big problem because it can be commuted through the circuit and it acts on the output in a simple way. And so again, we can try incorporating that correction into the relation itself, kind of in a similar way that we incorporated the classical post-processing that did the decoding for us. So what we end up is a new relation which now takes the input x, the measurement of all the physical qubits y at the end, as well as all these measurement outcomes s obtained during this logical state preparation step. And on the right-hand side, we have this function f. That function f is the action of this Pauli rec s once it's commuted through the circuit. That's the action on the output. Okay, I have not fully described how this works, but I guess you'll have to trust me. But what I do want to mention is that we have a new problem. I mean, this all sounds sort of okay, or I hope it does, but we actually have introduced a new problem, which is that in the presence of noise, it's not clear that this measure all code stabilizers trick is going to work. Why is that? Well, if we imagine measuring this register and getting some bit string s, but there were some measurement errors. So really the bit string was s plus epsilon. Then what we have on the first, the correction really should be rec of s plus epsilon, where epsilon is some low weight error. But we think that it's s. And the relationship between rec of s plus epsilon and rec of s could introduce a whole lot of errors. Like the difference between those two Paulis could be vast. In other words, the function rec s can spread one or a few small errors into many errors. And so for a general code, this does not work. There are codes where this does work, and those codes are the codes that admit single-shot, what's called single-shot logical state preparation. So this is going to be defined in the following picture. So here we have this, the m qubits of the code. We have some ancilla qubits. We apply this some constant depth circuit, and then imagine that an error acts on the output. Then we measure the second register. We get some s. And the remaining state of the first register should be the state that we want, which is rec s acting on 0 bar, up to some correctable error f. So the point is that when the error that acted before the measurement was correctable, meaning it was some stochastic noise with some low noise rate p, then the residual error after doing this noisy measurement and inferring s should also be described by local stochastic noise with some potentially larger but still reasonable noise rate. So this is not guaranteed for any code. You need a special code which has this single-shot logical state preparation property. Okay. So that is the description of how we try to get around these problems. So let me just summarize. We have the quantum circuit that solves one of these relation problems like the 1D magic square problem. It's a constant depth controlled Clifford circuit, and the input-output pairs satisfy some what we call the bare relation because we haven't made it noise tolerant yet. So this is R of xz equals 1. X is the input, z is the output. Then we define this noise tolerant relation, which is a different relation, R tilde. It's defined in terms of the old relation as well as two functions, the decoding function and this function f, which is defined via the single-shot state preparation procedure for the code. So this new relation incorporates information both about the original relation and about the error-correcting code. Note that we could have started from any relation defined by a constant depth controlled Clifford circuit. So this whole reduction will work not just for the 1D magic square problem, but also for earlier relation problems like this hidden linear function problem that we considered in our 2017 work. Okay, but the point is that the noise tolerant relation will be satisfied with high probability by a noisy implementation of a circuit where at the beginning you do all of these single-shot state preparations using your error-correcting code. then you apply the logical constant depth Clifford circuit, then you measure all the physical qubits, and you don't decode. There are some caveats, which is that you have to use a suitable code. I'll say at the end what I mean by that. Using a suitable code, it's enough to take the number of physical qubits per logical qubit to be polylogarithmic in n. And the noise rate has to be less than some constant threshold. Okay. So we have this whole recipe, which takes a relation defined by a controlled Clifford circuit and maps it to a noise-tolerant relation. And then what I described to you is a quantum circuit which, even in the presence of noise, will satisfy that noise-tolerant relation. But what is interesting is that the noise-tolerant relation is not much easier than the original one for classical circuits. So in other words, the lower bounds that you had for the original relation, like the 1D magic square problem or the other problems that were considered previously, can be easily mapped to a lower bound for this noise-tolerant relation. So we prove a lemma in our paper which relates to the following two things. One is the depth of a classical probabilistic circuit that solves the original relation R using gates of fan-in k, which is order max of m or m-nths. So those things, remember, are the number of encoded qubits per number of physical qubits per encoded qubit, and the number of ancilla qubits needed for logical state preparation. And both of those are polylogarithmic in n in the case of interest. And the second thing that it considers is the depth of a classical probabilistic circuit satisfying the noise-tolerant relation with gates of bound fan-in. That's the thing that we want to lower bound. We want to show that no classical circuit can satisfy the noise-tolerant relation without having a large depth. And so what we show is that this d tilde, the depth needed to satisfy the noise-tolerant relation, is really at least the original depth minus order 1. And the proof of this is fairly simple. What you do is you imagine that you have a circuit that outputs a triple satisfying the noise-tolerant relation, and then you post-process it to construct or to compute a pair satisfying the original relation, and you show that that post-processing does not have high depth if you allow yourself gates of this fan-in k. So I mentioned that in our case of interest, this k becomes polylogarithmic in n. And so we can just plug this into our depth lower bound on the noise-free 1D magic square problem that I showed you earlier. That says that this d that appears above is at least log some small number times n divided by 2 log k. And that's where this log n over log n comes from. So this gives us the asymptotic lower bound on the depth required by probabilistic classical circuits needed to solve the noise-tolerant relation. Okay, so just to summarize, we showed that the relation defined by a constant depth controlled Clifford circuit can be made noise-tolerant without making it much easier for classical circuits. But the whole construction relies on some family of error correcting codes that I did not argue exists. So now I want to tell you about that. What do we actually need in terms of the error correction? So what we need is an LDPC stabilizer code, which has constant depth Clifford generators, meaning you can implement logical Hadamard, phase, and CNOT gates with, it could be constant depth, but in our case, we're able to achieve depth 1 Clifford unitaries on the physical qubits. We need this single-shot logical state preparation property that I mentioned earlier. And the code should have an error threshold, meaning that like when you decode, it should be insensitive to local stochastic noise as long as the error rate is small enough. And we show that all of these conditions are satisfied by the surface code. And the first and the third one are kind of already known, but the new piece is the single-shot logical state preparation. And when I say we, I really mean my co-authors. And that is why I have only one slide about this, whereas it really could be an entire 1-hour talk. So you should ask my co-authors about this part of the paper. The single-shot logical state preparation in the surface code is really kind of an amazing thing. And it's a protocol that extends work by Rausendorf, Bravi, and Harrington from 2004. In that paper, the authors suggested that one should prepare a cluster state on a 3D grid perform 1-qubit measurements on all qubits except a subset of those on 2 opposing faces. Those are labeled B in this picture that I've reproduced here. And if you choose the measurement pattern on the qubits that are measured in the right way, then the state of the qubits in B will be a Bell state of 2 logical qubits encoded in surface codes on the boundaries. And this thing will work even in the presence of noise. And what is shown in our paper is that even if you have noisy measurements, you can do this in a single-shot fashion. And I think that's all that I'll say about that because I'm out of time. And also, that's all I prepared about it. The open problems, there's still several open problems related to this work. This is just a sampling, but almost anything that you might ask is open. One of the ones which I think is really intriguing is whether or not these algorithms provide a polynomial speed up in terms of gate complexity. Simulating Cliffords on a classical computer typically takes like n cubed time, or n to the omega time, whereas a constant depth Clifford circuit can be run on a quantum computer in linear time. So that is, understanding that is an interesting open question. Understanding whether or not these upper bounds on the depth, whether or not our depth lower bound is tight. Like, can you do better? And of course, the speed up that we have here in terms of depth is very mild, like log n versus constant. And is there some setting in which quantum non-locality might give rise to larger speed ups? I think that's an interesting question. So I'll end there. Thank you.
Great. Thank you, David. We have time for 1 or 2 questions.
So the error-correcting code properties are all satisfied by the surface code, but you talked a lot about LDPC codes, which are much more general. Would you gain anything if you had like good LDPC codes, maybe that had provable good distance? I mean, I know nobody knows if these exist or not, but have you thought about what you might be able to accomplish if you had them?
Well, maybe I can just say that one benefit we get from using the surface code is, again, this fact that we can do everything in 3D. So I mentioned that the single-shot state preparation can be done in 3D. But it's also true that there's some other tricks that let you implement the whole the noise-tolerant version of the 1D magic square problem all in 3 dimensions. And if there's these other constructions of codes that don't have geometric locality, and that would be a downside of using those ones. I'm not sure. I guess the short answer to your question is
I'm
I don't
asking
know.
if there's any parameter gains. So yeah, okay.
Yeah.
You would definitely lose locality if, presumably, you would. Actually, I think that's provable that you would lose locality if you had a LDPC code with good distance. But would you gain on any of the other parameters? Like, could you get rid of the log n? Or
oh, the log log.
Maybe that's not so interesting. But
yeah.
Are there other gains you might get?
I haven't really thought about it. Yeah, the log log is annoying, but what can you do? Yeah.
Maybe one more quick question. Well, if not, let's thank David again.